good.
I keep wanting to say Howard Hughes, but that was the...
Look it up right now.
No, I'm not going to look it up. I'll look it up in a bit. You get the point. The point is you get the
Right.
point. So what I'd rather see Americans or anybody do is measure data, right? Look at something concrete. In 244 today, we analyzed something, I call it the Florida motorcycle death rate, which is the proportion of death on Florida roads on motorcycles year to year. And the reason I look at that, when I look at Florida, is because it made the news about 3 or 4 years ago because Jeb Bush repealed the mandatory helmet law in Florida. This is when Jeb was governor. This is going back about 3 or 4 years now.
Yeah.
And there was an outcry. Oh my God, you want people to die. Take your helmets off. Take your helmets off. Take your helmets off. You want the... So I was like, okay, that's emotion speaking. That's emotion speaking. Have you looked at the numbers? I can't believe... Now, I would imagine somebody saying, I can't believe you want to look at numbers. I'm like, I can't believe you don't want to look at numbers. So we did. We looked at numbers, and we compared the motorcycle death rate. And the article that I pulled from the Gainesville Sun said 402 people died last year as due to motorcycle-related incidents. That's the most of any year on record. And I said, that interests me. That interests me. 402 deaths is the most deaths of any year on record. And I say, that makes me interested. That makes my ears perk up. So what I did was I formed a ratio. I formed a ratio in 1999 of not the number of deaths, but the proportion of death. Right? So number of deaths divided by number of registered bikes.
Right.
And I did the same thing in 2009, which is when this whole 402 came up. And guess what happened?
The same.
The rate went way down
Oh, okay.
in 2009. Which means you might have had more deaths in 2009, but what else?
You had more bikes.
Johnny, yes, Lloyd, you had more bikers in 2009. So imagine the numbers are much bigger than this, but imagine in 1999, 5 people died on motorcycles. And in 2009, 10 did. Oh my God, that's twice as many. Okay. But imagine in 1999, there were 6 bikes on the road. And in 2009, there were 100. All of a sudden, it's 83% down to 10%, right? It's more deaths, and I'm not trying to trivialize death. I'm not trying to trivialize death. I'm trying to look at the average of a whole population through a sample, and that tells you a very, very different story. I haven't heard back from my email sent to the Gainesville Sun yet. I'll let you know if I hear anything. I usually don't. I either get ignored or I get form letters that say thanks for playing. So, what makes me excited about stat classes is the fact that you guys are learning what questions to ask. That's what makes me excited. It's not that we can't individually change the world with data analysis, but you can question the world you live in and make people base what they're doing in reality. One of the worst things that this school ever did was put me on negotiations. Seriously. For years, they just ignored data for negotiations. I'm like, no. Well, we're going to keep pay equitable. I'm like, have you defined equitable? What do you mean? I'm like, what do you mean, what do I mean? How do you say equal? How do you say fair? How do you say the same as? How do you say top 1/3? These all seem like very simple things to us, right? After 6 weeks in class together. We know what a percentile is. You are in the minority. You're in the first percentile, I would imagine, of those who understand percentiles in this country. If that makes sense. Probably doesn't, actually. But that's okay. The point is that you know what questions to ask. And we're smack dab in the middle now of understanding, I think, one of my favorite tools in this class. And this was used all over the place in these polls, whether they were exit polls, whether they were just simple Gallup polls. This idea of a probability distribution. We were playing with this last time. We played with these in class on Tuesday. I gave you guys dice. We had a single die, we had double dice. I gave you coins last time too, and I decided not to do those. We'll just stick with dice for today, and then we'll stick with life insurance. 2 different distributions I want to play with today are gambling and life insurance, which, believe it or not, are both gambling. Exactly, they're both gambling if you think about it. What do you remember about these from Tuesday? And you can say nothing, of course, and just kind of...
They equal out over a period of time.
Say that again, Lloyd.
They equal out.
Oh, can I come back to that in 4.5 to 5 minutes?
Yeah.
Yes, I want to talk about the stabilization of the probabilities. Thank you, sir. Actually, believe it or not, I don't want to leave it with today's discussion either. Your next project, which is 2 weeks down the road, is all about the idea of witnessing random simulated behavior over a long period of time and seeing where things stabilize. Very, very good. Very, very good. Good. What else do you remember?
X and P of X.
Thank you, Eric. What are those? An X column and a P of X column? It diluted and distilled down to this, didn't it? It distilled down to this. What was that? What was this? Now, I know your project that you just survived, and I use that word not lightly because I know it was a lot of work for you, my mistake, did not involve this. Although what you calculated in that project was a part of these, believe it or not. Those little individual probabilities are part of this. We're going to use technology to aid us from now on and to get those, but now that you know how the inner workings work. What are these? Remember what these are called?
Events.
Good, good. The formal term is a random variable. They're definitely events. The formal term is a random variable. It's what can happen in an experiment. It's an event of an experiment. You run an experiment, and it's a listing of all the things that can happen in that experiment. So all the events. I love that word. Use it in a role word. That's even better, Tom. So it's an event number 1, event number 2, event number 3, and down to event number n. Beautiful. What's this column?
The probability that that happened.
Exactly. The probability of that event happening. And each event is going to have its own probability. Sometimes they're interesting, like a single die roll, where all the probabilities are the same. They're all equal. 1/6, 1/6, 1/6, 1/6. Sometimes they get more interesting, like a double die roll. 36, 236, 336, up to 636, then back down. Looks like that. If you graph it, it looks like that. Sometimes they're skewed. Sometimes they're bimodal. Sometimes they're they can take on all different shapes. And the rest of this class is going to be dealing with those different shapes and how they kind of show up in the commonalities. Good. Tell me something about all these. If you take them as a whole, yes, take you on. Yes, that's important to remember. You'll see why momentarily when you have to analyze your health insurance and your life insurance and things like that. I want to come back to that. I have an in-class quiz for us to play with today. And we'll finish class with that today. What else do you remember? I'm being intentionally vague with these. These will not be blank, obviously. These will actually have numbers in them for each individual experiment. So we'll build that as we go. What else do you remember? Sandra?
Those are the P with the X is empirical?
Oh, good. Thank you for that. This ties in what Lloyd just said about 2 minutes ago, too. They can be empirical, or they can be theoretical.
Or they can be theoretical.
Yeah, I like these more, generally speaking, because they're a little more realistic. That's what the pollsters try to do. Nate does it the best, but that's what the pollsters try to do by collecting the data, either through simulations or from a random sample, applying margins of error, and then giving us ranges of probabilities. The theoretical ones are a little bit trickier because you have to know everything that possibly could happen without error. And it's easy with dice. It's easy with a roulette wheel. It's easy playing craps. It's easy with a deck of cards. It's easy playing life with your kid. It's easy playing Yahtzee. It's easy for flipping a coin before a football game. We know what's going to happen with those events. It's not as easy saying what percent of the Oregon people are in favor of John Kitzhaber being governor. So it's easy to say 50%, because either they are or they are.
Yeah.
It's easy to say that. You're also well, actually, you might be correct. That might be pretty close. It might be close to half and half. Right? How did the election come out? Was it pretty close, Richardson, Kitzhaber?
No.
It wasn't. Oh, it wasn't 50-50. Okay, okay. But the point is that just because something has 2 outcomes doesn't mean they're 2 equal outcomes.
Right.
A coin flip is 50-50, right? A coin flip. But if I take a die and I hand it to Anna and I say, Anna, if you take a die, I never put it on my desk. I apologize. Roll a die. If you roll a 1, you get an A, and if you don't, you get an F. That's kind of a hell of a bet to take, right?
Right.
I say, what? It's 50-50. You either do or you don't. And Anna's like, no, it's 1680 whatever 7 because it's not equally weighted. And those non-equal weights are hard to establish unless you can theoretically know what they are. So I like empirical derivation of them myself. This is my personal opinion. Your next project, FYI, is all about that. It's all about counting huge numbers without having to count, which is nice. And it's all about using And it's all about using computer technology to simulate probabilities. One of my favorite ones is you're sitting 2 left of the dealer in a game of Texas Hold'em at the river. What's the chance you have a flush in your hand or will have a flush in your hand? It's an impossible question to answer theoretically. You can't answer it theoretically because you don't know what the other players have in their hands. So what you do is you simulate it hundreds of thousands of times with random assignations of cards, and you see how many of those times do you have a flush. That's the probability. Does that make sense? Ish. So Sandra, to answer your question, and it's tied into what Lloyd was talking about, this is great, but this is more realistic. The even more fun is when you can fuse them together, which we're about to do. We're going to
Oh.
fuse one with the other. Oh yeah, this gets good. This gets good. This gets good. We just did it in 244, kind of blew their mind. So, cool. So experiment number 3, I want to look at today. We did experiment number 1, experiment number 2. Let's do experiment number 3, which is a wonderful little game called Chuck-a-Luck. Chuck-a-Luck. This is going to have a sub-name, a subtitle, I guess, today of how to understand when you go to Vegas, you're going to leave with less money than you came with.
That's easy.
Well,